Welcome back to the lab. Another day, another power supply. Am I right? We've just finished designing the 2400 watt power factor corrected universal input AC to DC converter, which means that it's time to start designing the next piece of this architecture. The battery power module needs to do two things for our UPS. Manage a group of 4 series lead acid batteries while converting the power stored in our batteries to 425 volts when required. A voltage boost is necessary for this because we found it advantageous to keep the battery voltage below the safety extra low voltage limit of 60 volts. That means we don't have to think as hard about protecting the user from the batteries. Let's walk through the big picture because I want to show you where the next few videos are leading us. Here's what we have planned. This battery management power module has a couple externally accessible interfaces, 2 massive terminals that allow for pulling up to 60 amps out of our battery pack into the board. I haven't quite figured out how to do this yet, but we'll figure something out. I'm imagining some sort of massive power lug leading to an even larger wire. At any rate, these terminals will feed the UPS, and there are a few smaller terminals that enable battery balancing. Those are the only external interfaces. Everything else is internally connected to the UPS. And speaking of, wow, there's a lot of little circuits crammed into this module. Where to start? There's so many things to talk about. Yeah, I know. Let's start with those battery terminals. There are 2 major subsystems that connect to those battery terminals. This consists of a battery charging circuit, which has a complementary battery balancing circuit. The battery charger must be capable of 2 modes, a constant current and constant voltage charge mode. I'm not sure exactly how I want to implement this yet, but I'm picturing a constant voltage power supply that can be switched over to a less accurate but constant current mode. How can we change over from voltage to current regulation? Not exactly sure yet, but we'll tack a fun analog circuit into the feedback network of a regular power supply controller to enable switching between regulating voltage and current. There may be an off-the-shelf controller for this purpose, which will reduce the number of fun analog circuits designed into this module. I imagine that we'd probably use that controller if we can find one. The charger will handle most of the heavy lifting, but there's another feature required: cell balancing. If one of our batteries is charging faster than the others, our microcontroller requires a way to detect that and then slow that battery down so the other batteries can catch up. This is known as battery balancing. There is a monitoring portion of this circuit like we mentioned before, and the voltage monitors must allow for accurate and precise measurement of the voltage of any individual battery. That allows us to detect if that battery is above or below the others. This information is then fed into the battery-controlled logic. This could be implemented as 4 analog inputs as shown in our diagram, but it could also be 1 analog input and some digital inputs. It may prove more convenient to create some analog circuits that determine which cells require balancing, then communicates that information with the microcontroller via digital signaling. That could let us know when any individual battery requires balance. I'm leaning towards 4 analog inputs at the moment, if for no other reason, because it allows for ensuring that cells are neither overcharged nor over-discharged. Battery balancing can happen in a couple different ways, but 2 methods are by far the most common. We can either use a lossy method, which adds resistors across each individual battery to slow down its charging process, which is a cheap and effective method, but if we're feeling a little more advanced, we can replace the resistors with what is effectively a flyback converter with a single primary and 1 secondary winding for each battery. This converter draws power off the whole battery stack and redistributes that energy inversely proportional to the cell voltage. That is, it pulls equal current out of all of them and then shoves it back into the battery with the lowest voltage. This effectively takes some energy out of the most charged cells and redistributes that energy more evenly across the cells. You may be wondering why less current flows through the balance connector, and the reason why is fairly simple. The balance connector only carries the currents that flow when balancing the batteries. They do not carry any of the charge or discharge current, and that saves a bit of complication. It makes that connector a lot cheaper. The specific method we choose to implement for battery balancing isn't critical right now. What's important is that battery balancing exists. Objectively, there's a lot going on in this microcontroller. It's keeping an eye on a lot of activity and wearing a lot of hats. If we can lighten the computational workload by reducing the amount of math required to monitor and control battery systems, that may enable using a significantly cheaper microcontroller for these functions. After all, there isn't really any time-critical processing tasks going on here. We'll always need 2 analog voltages, so we know there's some level of ADC processing required. And at the very least, we need to know the total battery stack voltage and the current flowing in or out of the pack. This knowledge allows the battery management system to verify that the charger isn't overcharging the batteries connected to the UPS and more accurately determine how much power is left in those batteries. I feel like we've covered battery management on the charging side of things pretty well, so what about discharging? This is where things really start to heat up. Power flows from the batteries through the input power filter and eventually ends up in two circuits. One of these is the DC to DC converter that steps up the battery voltage to 425 volts DC, and the other is a switch mode power supply that backfeeds 24 volt power to the UPS itself when the mains has failed, keeping the lights on, so to speak. It's important that this second power supply, the one sourcing 24 volts, is never active when the mainboard does not expect it to be. So we'll require two enable signals, one from the microcontroller and one from the mainboard. Both enable signals must be present for this power supply to come online. Both microcontrollers need to decide that we need to enable 24 volts. The full H converter needs to push 2400 watts through it while stepping up the minimum battery voltage, 32 volts, up to 350. This requires a turns ratio of 11 at the very least. This turns into a small issue for our system. The square wave we're rectifying will have an amplitude of 352 volts at the minimum, which isn't quite enough, and 638 volts at the maximum DC input voltage. That means that the existing silicon carbide rectifiers that we're using, man, those diodes really have their backs up against the wall. Only 12 volts of margin from normal operation to catastrophic failure. Makes me a little nervous considering the 600 volts underneath it. Perhaps we can leverage a bit of synchronous rectification to keep losses low. Either that or select some diodes with higher voltage rating. It's an interesting challenge for sure, and I can't wait to find out how we tackle this one. The power supply will use MOSFETs on the low voltage side, the battery side. That means that we'll need one more voltage to drive this supply correctly. A 15 volt supply that gives the isolated gate driver what it needs on the low voltage side. Since we're on the low voltage side and don't need a lot of current, this may very well just be a 15 volt linear regulator dropping 24 volts down to 15. I'm still open to a switching converter, but that seems a little excessive, so I'm leaning towards linear because I don't think this will be worth dropping down another instance of our flyback converter. Linear regulators are simple, cheap, and the current required for this is very small. Space is limited, cost is limited, time is limited. I need to use what we have wisely. While the FETs are on the low voltage side, the controller for this power supply lives in the DC bus isolation region for convenience. We need 5 kilovolts between that and the low voltage side. The isolated analog voltage feedback gives me a little more anxiety than isolated gate drive. I've had a great experience with the ISO drivers from Silicon Labs before, and I expect this will be no different. There's just something about connecting analog voltage feedback across an isolation barrier that screams, potential phase delay and source of error. I don't know. Maybe I'm paranoid. We've covered all things power, which is great. Jumping into a couple easy items to finish this off, we'll use the same fan control and tachometer monitor circuit as the PFC module. Our microcontroller has some signals controlling all the functions we just mentioned, plus a couple to interface with the full H converter. Now that interface is dead simple. Just a couple I/O lines, a go button, and a signal that indicates everything is fine. All told, we'll need around 29 I/O for the battery microcontroller, and this controller performs a few critical functions. It monitors the state of health for the connected battery stack, estimating ESR and monitoring how capacity changes over time. This battery manager controls charging and balancing logic while calculating power flowing in or out of the batteries. Naturally, the microcontroller also reports status of all of these things back to the master controller via the serial communication bus. Boom, check, done. Architecture planning complete. You may have noticed there is almost zero overlap between this architecture and what we built for the Phase 1 design. Well, our battery pack changed from 2 batteries to 4. The balanced current is now around 1 amp instead of 0.1 amps. The charge power has more than tripled, now approaching 100 watts. We can monitor DC power entering and leaving the batteries, and the push-pull converter has been replaced by a full H. Despite the small mountain of work I just made for myself, I think this architecture will be a massive improvement over what we built for Phase 1. Maybe we should just call that the prototype? I don't know. Precise monitoring control of a system is very satisfying, and that's what we're striving for. Precision. If you like what you saw today and you can't wait to see this design take form, consider subscribing to be notified of our future videos. Up next, we'll be talking about using MOSFETs in parallel and design the switch mode power supply transformer that will be used in the power supply we were just talking about to step up 48 volts to 350. If you think this UPS is awesome, let me know by hitting the like button on this video, giving us a shout on Twitter, or leaving a comment letting us know what you enjoyed. Most of all, I hope that you learned something great today, and I hope to see you again soon. Thanks for watching EE for Everyone, and thank you for staying till the end. Bye!